Today we are walking through the paper titled AdaJEPA. This paper is about making latent world models adapt while they are being used for planning, instead of freezing them after offline training.
So the issue is not planning itself, but that the planner trusts a model that may be wrong during deployment.
Exactly. The planner rolls out the learned model, chooses actions, and then the real environment may respond differently from what the model imagined. Under shifts like changed physics or unseen object shapes, that prediction error can send the plan off course.
What does AdaJEPA change in that loop?
AdaJEPA turns each real transition into a self-supervised correction signal. It plans with the current model, executes the first action, observes the next state, updates a small part of the model, and then replans with the adapted model.
The replay buffer in the diagram is storing transitions from the same episode, right?
Right. Each episode starts from the pre-trained model, keeps its own buffer, and uses the transitions caused by its own actions. That is why the method does not need new expert demonstrations at test time. Here is the planning side. The observation and goal are encoded into latent states. The predictor rolls forward possible actions, and the planner scores them by how close the predicted future latent state gets to the goal latent state.
Can you define the latent quantities before the equations get dense?
The current observation becomes ET, the action becomes UT, and the predictor uses those two latent inputs to estimate the next latent state. This is the compact state transition that planning relies on. During offline training, the model learns by making its predicted future latent states match target latent states. The prediction loss averages those mismatches over a rollout horizon.
So test time adaptation is not a new reward signal. It is another prediction error signal from the real transition?
Yes. The adaptation loss compares the model's predicted next latent state with the encoded next observation that actually happened. The stop gradient target keeps the correction focused on making the predictor and chosen encoder parameters fit the observed transition. Then AdaJEPA updates only the selected parameter subset omega by a small gradient step. The paper emphasizes that this can be lightweight in experiments. One gradient step per MPC ray plan is already enough for strong gains.
What experiments make that claim convincing?
The paper tests goal-reaching tasks under several shifts. Push OBJ changes object shapes or visual appearance. Point maze changes dynamics, like low mass or high damping, and also tests held-out maze layouts. First, look at point maze with the normal dynamics. The frozen model reaches the goal because its learned dynamics match the test environment closely enough.
The path bends, but it still ends at the goal.
With low mass, the same force moves the agent faster than the frozen model expects. The planned path overshoots near the goal, and the frozen world model fails because its predictions no longer match the actual dynamics. When AdaJEPA adapts during the same kind of shifted environment, the trajectory recovers. The important comparison is frozen low mass failing versus adaptive low mass succeeding.
Is the improvement only visible in single examples, or does it show up in success rates too?
It shows up in success rates across the reported settings. The paper says AdaJEPA consistently improves planning under shape shift, visual shifts, dynamic shifts, and layout shifts, using only a single adaptation step at each MPC ray planning step. The ablations make the effect more concrete. On push OBJ, adaptation improves success on a scene T-shape from 50% to 88%, and on a held-out square from 20% to 51%.
Does updating the model make planning too slow?
The paper argues that the extra latency is small because the update touches only a small subset of parameters and uses only one step. It can also reduce the number of ray plans because the agent reaches the goal in equal or fewer ray planning rounds.
What is the limitation?
AdaJEPA is a lightweight correction method. If the test environment needs features missing from training, adaptation can help, but it may not fully close the gap.
So the takeaway is that the model keeps learning from the consequences of its own plans.
Yes. AdaJEPA's main contribution is closing the loop between planning and model correction. The agent plans, acts, observes what actually happened, adapts the latent world model, and replans with a model that is better matched to the current environment. That wraps up this paper walkthrough.